5. Yes. So we have natural log over the square root of x plus 3. And that is 1. Perfect. Same idea. Now if I didn't have natural log in front, then the domain would have been this for the square root. We know that. The quantity on the square root has to be greater than or equal to 0. But I have log. Because I have log, I cannot have 0. So now the restriction is this. So that x greater than negative 3. So the common domain, although there is only one function here, is negative 3 to infinity. If I don't get a solution between negative 3 to infinity, I'm going to conclude exactly what we concluded before in that case. Okay, so still here I have no choice. I shouldn't say I have no choice. This is the method I recommend. E, that's the base of natural log, raised to the first power, which is just e, equals the square root of x plus 3. Now this equation is what type? Can anyone tell us? And this is a number. Can anyone tell us what type of equation is this? Very good pick, Kayla. Thank you. What type of equation is it? And the answer is?
Square root?
Yes. Great job. So then we have to square both sides. We have to use the inverse operation or the inverse function. Then we have x plus 3 equals e squared, or x equals e squared minus 3. If you have any doubts, you can always check this to be in here. How do I check? Here is the key for e, right here. The same key with natural log. So second and e, I didn't mean that. Second and e to the x, which is 2, power 2, and then come down and minus 3, and you will see this is 4.38, which is definitely a positive number greater than negative 3. So I will say yes to this one. Very good. Anything else from here before we continue?
So, like, when we're doing these on the test, we would just get to the bottom and, like, it would just be yes or no solution?
You will have to enter this.
Right.
Yes.
But, okay.
It may ask you to, yes, the question may be, if there is an answer, put it in. If there is no answer, check there is no answer, or the equation has no solutions. Yes.
Okay.
So by setting x equal, you're agreeing that it's yes, otherwise you would put no solution.
Yes, because this number we checked and it's in the common domain, or in the domain. If this number is where, for example, negative 4, I would have said no solutions, because negative 4 is not between negative 3 and infinity. Does it make sense? Okay. Okay, so we have about 15 minutes. I would like to start the last section of this chapter. More applications. This is the last one of chapter 4. So 4.5 applications. The models will be given to you, but I just want to talk about the models for a moment. The models mean the function. You don't have to memorize anything here. You have to understand what they mean, but not. Okay, so one very important application, a group of applications, I should say, exponential growth. What grows exponentially? Rats, bats, bacteria, rabbits, people. Maybe after this virus, maybe not anymore. I'm kidding. And so on and so forth. Number 2, exponential decay. What decays exponentially? radioactive substances. And other. For example, birds. Endangered species. Here, birds grow exponentially, but some birds that are endangered species can decrease their number. We hear about a lot of animal, birds, fish that are endangered species. They follow an exponential decay, not an exponential growth. Okay, also I can add here fish. But again, if something happens in their life and they don't reproduce, or they are killed in large numbers, then their livelihood changes from an exponential growth, meaning this, like the virus in people, into this, like decreasing, exponential decay. So it depends. And the third group of applications is logistic. I'm not sure what's happening here with these pages. So logistic growth model. All will be given to you. But let me just show the first two, because these are multiple different models. But let me just show you the first two. The first one is about number of birds, number of fish. Also, this one can be a function of a number, right? So for number one, for the exponential growth, it's a function of time. I'll identify each and label each letter in a moment. E to kt. This is the amount at time t. What do you think this is? A0. The initial number. E is our best friend E. K, growth rate. And T is time. In number two, this one, our best friend, this one.
Oh, okay. Sorry.
We establish now in this chapter a best friend. It's E. Okay, so the second one, which is the exponential decay, deals with mass in general. What's the difference? Just the notation. And this one has plus because it's a growth, and this one has minus because it's a decay. Now this time m of t is the mass at time t, m0, the initial mass. K and T are the same thing. But this time is not the growth rate, but the decay rate. So K, decay rate, and T time. Okay. These we've seen before, we're going to work on, but I just want to show you the third model. We have time to look at one problem with the third model, which is the logistic growth model. So if you have your book, I'd like to start with 43-44, page 531. We are given a function. The function given in the problem is p of x equals 90 divided by 1 plus 271 times e to negative 0.172x. I'm checking that I copied, it's 122x, sorry. 122x. P of x is the percentage of Americans who are X years old, so X is age. I take notes as I read. X years old with some coronary heart disease. Use the function to solve 43 through 46. We chose 43 and 44. What percentage of 20-year-olds, so in 43, what percentage of 43-year-olds have some coronary heart disease? I meant 20, of course. And 44, what percentage of 80-year-olds? I need to put this book away. Okay, and 44, what percentage of 80-year-olds have some coronary heart disease according to the model? What am I asked to do?
P of 20 and P of 80?
Excellent. So P of 20, P of 80. Since I have two numbers, I'm not going to do this twice. I'm going to put in the graphing calculator. So in y equals, clear? 90 is okay, it's safe because it's just one number. Otherwise I would have put in parentheses. So 90 is okay. Divide by, now we need parentheses. Careful, 1 plus 271. Now we have to use the E key, second and E. The power is negative 0.122x. Please put it in parentheses and use this negative. Negative 0.122x. Close the parenthesis for the power. Come down to close the parenthesis for the denominator. Are we done with this, with entering it? Is this okay, everyone?
Real quick, what did you put between 271 and E to make it more clear?
Nothing. It considered as a product.
Okay.
Yep. So now we go to second and table, and I'm going to plug in 20, press enter, and I'm going to plug in 80 and press enter. And here are my answers. 3.7, this is percent, that's the measurement unit. And for 80, look at that, 88.6. According to the model, people in their 80s, a huge number, a huge percentage of them, almost 89% of them have some coronary heart disease according to the model. People like you in your 20s are very unlikely for you to have a heart disease situation. Okay, I put the book away, but I think we have time for one more. I don't want to go to the other models because I need to explain certain things. It's not a plug and chuck situation. Okay. Maybe we should look at one more log equation instead of rushing through a word problem. Let's look at 64 on page 515. And the problem is 7 plus 3 natural log x equals 6. Okay. We want to solve for x, but first we have to state the very important restriction. That x has to be a positive number. The next step, I hope you agree, we have to clean it up. So then 3 natural log x equals -1. We still haven't cleaned it up fully. What should I do next? So I moved 7 to the other side. But now I have one more step before I change it into an exponential. I divide by 3. Natural log x equals -1/3. Only now I can change it into an exponential equation. Knowing that the base is e raised to this power equals x. So x equals 1 over e to 1/3, or x is 1 over the cube root of e. Since this number is definitely greater than 0, I found the solution.